Thanks a lot, Nicholas. And yeah, let's just say thanks again for the opportunity to present and share about our work here at ClydeSpace. Hey everyone, my name is Lian Ming Goh. I'm a satellite systems engineer at ClydeSpace. You can just call me Ming for short. And for the next 30 minutes, I'll be sharing with you a bit about our work here around constellation satellite design through model-based systems engineering. This is the agenda to go through a bit about our company and the project that I'm working on to improve space data as a service. Then we'll dive in straight into the main content, starting with a bit of a discussion around document-based systems engineering versus model-based systems engineering, and looking at a single satellite model, then walk through an example concept of what a constellation system model could look like. And I'll wrap up with a short summary. So a bit of an introduction, and our company has a vision is that space should be accessible, useful, and affordable to the benefit of all citizens of Earth. We are, as was introduced earlier, a world leader in small satellite technology and services, spanning across 6 sites in 5 countries on 3 continents. So just skipping a bit on the numbers there, if I like to direct your attention to the background on the image here, what you can see there is one of our satellite Seahawk platform. So I'm not sure whether it's showing good enough on the screen on your side, but if you can see on the shorelines, there are a little bit of a different color and different shades of green and blue. That's the algae bloom that is being imaged. And that's the mission of the Seahawk satellite platform. It is to provide support to the maritime environment, marine environment. And the small red color circle there is where I am actually situated to share this presentation with you up in the Scottish Lands in Glasgow. We have 3 divisions for our company. First and foremost, we produce space products and components, battery packs, solar cells, onboard computers, ADCS sensors and actuators, star trackers, you name it, we've got it. The second part of the division is about space mission, where we have a fully assembled satellite platform that can be integrated and accommodate a variety of payloads. And the third division, which is the main focus of my presentation today, is on space data as a service, where we start delivering high quality, timely data from space to clients. So you might not notice, or you notice already, depending where you are from in the space sector or not part of the space sector, space is quite integral to our everyday lives. Just to give the most basic example of all is GPS and navigation system. To all my friends who, quote unquote, being directionally challenged, then you probably wouldn't be able to survive without any navigation system nowadays. Or if we look at Earth observation applications, start monitoring our Mother Earth here, we can start detecting wildfires, measure air pollutions, monitor water quality, like what I just mentioned there about our Seahawk mission, provide precision farming, and so on and so forth. The other side of this is also, if we look at the recent OneWeb Starlink type, is really focusing on the communications side of things, or even just the fundamental TV broadband, is looking at satellite communications applications, and we can further kind of extrapolate the insights into, if we deploy a constellation, then we can start looking at autonomous shipping, autonomous smart applications, smart cities and whatnot. So this is where then my project comes into play. The expansion project is to develop a constellation-ready spacecraft design. We are preparing for high volume production, constellation operation, data delivery, and it's a 3-year project to prepare and deploy 10 spacecraft as part of the initial deployment. Looking at the whole value chain, we are partnering up with 6 different partners, and ESA is co-funding this project. At the start, we have mission design and analysis, looking at how we integrate inter-satellite link systems, autonomous routing algorithms into our spacecraft to be constellation ready. We are looking at how to incorporate design for tests, design for manufacture methodologies, learning a lot from the automotive and aerospace industries, how to optimize our production processes. We are looking into flexible way of operating a multi-mission, multi-constellation network, and also streamlining our launch processes and launch license. And also we are developing and establishing a user-friendly API system to engage with our customers for rapid mission data access. Then off the back of this will be 10 initial spacecraft, 4 of which we are hoping to launch it through the UK launch. Now there's a fundamental part where I haven't touched on, which I'll touch on now, which is all the bits and pieces you can see here. A lot of the complexities that is involved is being underpinned and being integrated in a model-based engineering approach. What this means is that at the core of everything, there's a system meta model connecting and propagating all of the information, all the changes throughout the business value chain, as you can see here, just going clockwise, satellite constellation, integrating and communicating with the ground station networks, constellation operational platform, and customer interfacing. On the other hand, we need to think about constellation redundancies, our replenishment strategies of our satellites, and all of this information is being backed by the system meta model. So that concludes the initial introduction of the project. Now I'll dive into the main content. As a systems engineer, I feel it's only right if I start with the most basic diagrams here. If you're a systems engineer like myself, and also in the UK, European side of this, you might see this very familiar, particularly the ECSS standard from ESA at the center, talking about the systems engineering scope of work and how we interface with the rest of the domains. At the right side is a very classic V model of the systems development process. So as you can see here, as we step through the different life cycle and different phases of the project, it requires a very meticulous, detail-oriented, and structured documentation. There are extensive reviews, requirements review, preliminary design review, PDR, CDR, test reviews, qualification reviews. A lot of this hangs on having good documentation to pass the design, essentially to pass the review, essentially. And people treat documents by default as information databases. So I'm just showing a cartoon here about a likely failure, a systems engineering failure of what it would look like, what the proposal promised, starting with the top left, and what the manager might interpret it to be, what the engineer might design slightly out of spec, maybe what the analysis simulation engineer go and analyze different variant cases. The documentations are kept minimal, and the manufacturer tries his best understanding to manufacture something after a rework looks fancy, but really what the customer wants is something different. So the understanding and communication is really a key part of what we know of systems engineering today. And let's look at the model-based way instead. At the bottom left, you see the definition from INCOSE, International Council of Systems Engineering. MBSE is the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout development and later lifecycle phases. What this essentially means is, if you look at the central diagram, system architecture starts becoming central and is linking everything up from requirements to your CAD model, your bill of materials, your supply chain management, your high fidelity performance simulations, all through to documentation to be produced automatically with a click. The same V model on the right is really showing, as we step through the process to the right, if you find any faults and any defects, the later you find it, the more cost it will be to fix those errors and those issues, particularly if it is design issues. So the sooner you find defects, the sooner you detect things, detect problems, the much more affordable it is. And to do this, we have to have accurate, highly descriptive, and content-rich architectures. The MBSE language, methodology, and tool used will enforce consistency, quality, and traceability already. We are treating models by default as information databases. And just to swap in the tree story earlier, what you're seeing here is a system meta model that is being integrated with the rest of the other models like requirement, functional, behavioral, performance, structure, component, any other engineering or non-engineering model you can think of is being tightly integrated into one. And if we look at such an integrated model, the understanding of scope and the understanding of interfaces within each submodels is becoming very important, and also the communication of mindset, which I'll touch on a bit later about this. So just talking a bit about the system model, I want to share a bit about, there's two different types of system model. One is a system descriptive model, and another one is a system analytical model. A descriptive model is static by nature, whereas analytical is dynamic by nature. A descriptive model, you use it to describe, formulate, specify the system. You describe the scenarios, your use cases. For my friends or colleagues who like to use visual, move pixel by pixel to draw diagrams and interface on your power lines, your control lines, your bus lines, draw your ConOps and things like that. Those are, you're describing things in a diagram, so it's a description. Whereas analytical model is used to compute, calculate, evaluate the system. Your typical power budget analysis, link budget analysis, delta V budget analysis. So all of this analysis that computes things is an analytical model. Descriptive model allows understanding of the system interrelationships, whereas the analytical model allows us to understand system performance. Now, I talked about visual diagrams earlier. Those are unconnected diagrams. Visually, those are diagrams. It's just there at the back of it. There's nothing connected to it, so it's document based. And if you want to change something, you would have to propagate however many diagrams you have to change that. And for analytical models, although they are powerful in itself, we have a lot of industrial tools already, but they also exist as standalone domain-specific models. If you are staying within the domain itself, that's fine. But as systems engineers, you really need to focus on the interfaces and how everything connects as a whole. You're looking at connecting the dots. You're not looking at just one single domain in isolation. That's not the case for systems engineers. So in a well-integrated design and analytical model, we're really looking at automatically propagating changes. We are really looking at automatically feeding inputs and feeding outputs here and there. So descriptive models, I would say, are for systems engineers to own, and then you would then use MBSE to propagate and connect the design models and the analysis models. So looking at a single satellite system, where just a recap of this system meta model diagram, if you take one satellite and put it into describing a model, at the right side, there is all of our very familiar software tools and industrial engineering tools that we use to compute analysis. The problems, as I mentioned earlier, those are standalone tools requiring manual importing of data. The risk of inconsistency is quite high. You might have your thermal engineers baselining the different assumptions that your power engineers are baselining for orbital analysis and whatnot. You might have your mechanical engineers having a different reference frame definition to your pointing AOCS engineer, which is not good. So it takes design iterations, takes time, it's challenging to manage. But if we start bridging the gap between design and analysis, and these two models come into play, describing the requirements in, tying in the component and product model, tying the test model, what we are seeing here is there's an ease of traceability, there's lower risk of inconsistencies, and we can run trade-off analysis much faster in a shorter period of time because we have kind of reduced the miscommunication that's there. And we can easily extend this to a constellation model, which I will now step through a few examples with you. So the same diagram we showed earlier, taking as a constellation now, what you are seeing here is I have described at the light blue color different external actors that is interacting with the overall constellation system model. I'm treating the constellation level as a single entity. I don't care necessarily what happens within the constellation system just now. It's really looking at outwards, it's really looking at the external interfaces. So the three external actors on the light blue color has the interfaces defined at this stage and treating the main system as a black box. And once we look at the interaction of the external interfaces, just giving one example on the red color arrow there, the space data is being provided through the space to ground comms protocol. The direction of exchange is from the constellation system to the ground target. Very simple, visually representative architecture that says a lot about this. And the same is for all the other interfaces. Once we are happy with the looking outwards side of things, then we start looking inwards, looking at decomposing the main system. Skipping a few bits, here I have broken up into two parts. One is the CubeSat constellation, one is the ground station network. And notice that the external actor at the far right-hand side is still the same. I have not touched that. That's not being decomposed because that's not the main interest. I am also describing the red color circles. You can see there a few interlinks within the main system. And the green color circles will be the interesting part, which I'll touch on very soon, on how we bridge the gap between descriptive and analytical models. A question to throw out here, just food for thought, is do you think whether these behaviors are appropriately described? Like, they immediately, even though the diagram right now is very simple, there's not much content yet, but we can already start to critically assess whether the system as a whole is appropriately being designed or not. Is the CubeSat constellation only having 3 such behaviors? Is the ground station network only having 2 such behaviors? Why this is important? Because this would inform our kind of like ConOps, concept of operations. This would inform the different operational modes we might have in the system, for example, and things like that. So these are things we can already start thinking about, and the systems engineer can already start the technical discussion with any relevant engineers or stakeholders already at such a high level. If we are happy with that, just to take an example forward, then what you're seeing here on the left side is the green color circles where I have described and added parameters. This is where systems engineers, then we can start using all these numerical values that our analysis engineers so likes to use as inputs, throw it to them, chunk through their analysis, and come back to us. We update the values and things like that. To orbital analysis is the example that I'm showing you here. There's a 25 satellite constellation with 5 orbital planes. There's a solar flux assumption. There's an Earth radius assumption. There's an orbital propagator assumption for running through the analysis. The same can be described for SolidWorks 3D CAD model. The same can be described for thermal models, heat dissipation, the space environment model. and any sort of tools, basically. And you are reaching the boundary between descriptive and analytical model at this stage. So just stepping back a bit, looking internally now, you can see I've added more functions. It's the same practice I showed earlier. And the same red color arrow is the same example of the function. It is describing more about the interaction within the main system. So if you trace the green color line, green color functional chain, logically, the space data is provided through the application-specific data protocol. I've added a physical implementation, which it constrains it within, for example, the 5G frequency bands. And you can see requirements are already embedded into the design descriptive model at this stage. So I'll just stop here for now. The system architecture, this one architecture diagram we're looking at, it is very rich. It contains a lot of information already. If you don't know, let me just summarize it. Number one is it contains the component breakdown of the main system. It has been broken down into CubeSat, ground station network. It can be broken down to more, but I'm just showing two examples here. Then it's breaking it. It's describing the behavior, the logical behavior of the system, and that informs your concept of operations. That informs your modes, operational modes, and things like that. And there is also parameters that are being described to use it for mission analysis, to use it for any of the systems analysis. There is also interfaces that we have looked at. I didn't mention it, but the interface between ground station and CubeSat that's being assumed to be S-band frequency. Is that right? Is that wrong? You know, those are the interfaces that perhaps the comms engineer, the RF engineer can start taking into place already and start considering. And the functional chains that goes in between, I've described 3 functional chains, red, blue, and green. The black color line just shows overlapping ones. So the functional chain, if we look at one chain by itself, it allows us to step through the functional chain. You can start looking at communicating with the software engineers to describe software architectures. How does each function and each logical behavior operates together? What is the mode transition between them? What is the triggering point to move from one function to the next? And how does faults come into play? This is where then FDAR mechanism starts coming into play. So there's a lot we can start thinking and start facilitating the technical discussion just on a very simple architecture diagram at a high level here. So that's one more question that I want to throw it off. I know that's a lot already. Just ending this example here. Can this function and behavior be represented in a single CubeSat or a ground station node? I so far have only shown the constellation system, not treating any one single satellite to pin it out. But if we look at each of the functions that's being executed here, can it be done using a single satellite? So that's another question that is very interesting to answer. And there's many different applications. There's many different ways to answering it, because you really have to consider specific applications of your constellation. Are you a formation flying type, swarm type constellation? We are looking at real-time dynamic monitoring the behavior and the states of each and every nodes, or a mega constellation where the sheer volume of satellite nodes and ground station nodes you need to operate from an operational standpoint is very challenging. The capability of the MBSE tool to support such a system of system modeling is another question. Any sort of emerging behaviors? Do you need to consider distributed decision-making capabilities? What's the level of autonomy? What's the security threat model be like? And how does this whole thing impact the service availability from a space data as a service standpoint? The interdependencies of individual systems and subsystems within the constellation is important to understand, and how this interaction change with external factors and internal mode transitions. There's a lot to consider here. but I hope you can see where this is going with such a simple diagram that I'm just showing. So a summary, we have to be clear. The lessons learned is we have to be clear on the architecture boundary, what information is within the descriptive model versus analytical model. We have to agree on the use of terminology, agree on a common way to use MBSE tools, language, and methodology. We might want to have a standard operating procedure produced at the end of the day for everyone to follow. And very importantly, model down to only a level of detail that is useful. Just again, the same example we stepped through earlier, we can go so much into detail, but is it ultimately useful? Not everything, not every detail will be useful for system engineers to communicate outwards and looking at interconnections. The future work is we will be testing it and flying it for an in-orbit demonstration mission. I'll leave you to read the model-based MBSE adoption. We have to be mindful of the modeling competency and allocation of resource. Lastly, I'd just like to leave you with this slide here. MBSE is still fundamentally systems engineering, but a potentially better way of implementing SE practices and processes. Information is stored as models and is maintained as a single source of truth for all stakeholders. You produce documents automatically. That means you don't need to spend time writing and perfecting the wording, but you spend time focusing on the actual design integrity of the model. Again, the example I gave earlier, we are spending time questioning things, whether it's right or wrong, describing it right or wrong in a diagrammatic, visual friendly way. And just leaving a quote here, a picture is worth 1,000 words. We've heard this a lot, but personally, I think a connected diagram is worth £1,000,000. Thank you for listening, and I hope you enjoyed the presentation.